Okay, this is what we're going to do today. We're going to talk about isosceles and equilateral triangles. So let's see. What do we have? This must be what kind of a triangle here? It has two congruent sides, so this must be an isosceles triangle. Okay, isosceles triangles have, of course, two congruent sides. They have, from before, two congruent angles, but that's not going to really help us finding the area. Just good information to remember from before. So the height of an isosceles triangle, let's draw that in here. The height of your isosceles triangle goes from the vertex across from, we'll call this the base just for fun today. But remember, any of them can be the base. So this is particularly and only true for the height that comes from the vertex. And 89.413% of the time, that's going to be the height that we are talking about, is the one that comes from the vertex. So it comes down like this, and it intersects at a 90-degree angle. Okay, so this is the height for your, well, it's for all of your triangles, but in particular your isosceles triangle. Okay, now for an isosceles triangle, this does some pretty special things. Okay, it's also called the perpendicular, wow, that's kind of wide for my purposes right now. It's also called the perpendicular bisector. Okay, so the height of an isosceles triangle is called the perpendicular bisector. Okay, hopefully you know what these two words mean, right? What does it mean to be perpendicular? At a 90-degree angle, so intersecting at a 90-degree angle, check, right? We see that here. All heights intersect at 90-degree angles, but it's also a bisector. So what is it bisecting? The base down here. So it cuts your base into two exact parts, right? It cuts it intersects the base at a 90-degree angle. Okay, as all heights do. All heights intersect at a 90-degree angle, but it also intersects the base in the exact middle. Okay, so the height for an isosceles triangle is a 90-degree, so perpendicular, but it is also a bisector of the base. Okay, so what kind of triangles are formed by this perpendicular bisector? Well, if we were to read, there are two congruent triangles. And what kind of triangles are there? Right triangles. There are two congruent right triangles formed every time you have a height. Triangles. Two congruent right triangles. And whose theorem are we going to use to calculate the height? The only theorem we use every single day, the Pythagorean theorem. Okay, we've used it a lot so far, and we're going to continue to use the Pythagorean theorem when we are calculating things about our triangles. Mostly it's going to help us find the height / base. Okay, sometimes, like yesterday's problems, we had a right triangle where you knew the height and you could find the base, or vice versa. So we use Pythagoras a lot. So example number nothing here, and there's no example number, but it says find the area of these triangles. Okay, so which of these two sides, 13 or 10, is your base? 10. So 10 is your base, and we need to find the corresponding height that goes along with that base. So you draw your vertical line. Okay, this is the height. And what do we know about the bottom part of that right triangle now? That this much right here is 5. Okay, only with an isosceles right triangle or an isosceles triangle is the height bisecting the opposite side. Okay, so we can calculate the h by using the Pythagorean theorem. So what would that look like? 5 squared plus h squared equals 13 squared. So So when we solve this Pythagorean theorem for h, we get a height of 12, okay, which is exactly the information that we need in order to calculate the area. So area is 1/2 of the base is 10, times the height that we just calculated, which is 12. So 1/2 of 10 times 12, I believe, is 60 square centimeters. Okay, this one over here. So here, our height goes from the vertex, right, in between your parallel legs to the opposite side. So in this case, 6 is your base. And we know that it bisects 6, so this half is going to be 3. So we're going to once again use the Pythagorean theorem in order to calculate the height of our triangle. So 3 squared plus h squared equals 14 squared. Okay, now 9 is 3 squared. 14 squared is 196. So when we subtract 9 from both sides, we get 187. Okay, and finally, taking the square roots, the height of this triangle is the square root of 187, which I don't know what that is off the top of my head. And that's okay if you don't either. Okay? You don't have to write down what the exact height is on your piece of paper or as a decimal. Right? You don't actually have to calculate that at all. What you do have to calculate, though, is the area. So area is 1/2 of 6, right? We're finding the triangle, the whole entire triangle. Okay, so we have to go to the whole entire base again, right? So we're not calculating the base with the triangle with a base of 3. We're calculating the whole entire triangle, so we have to use the whole base of 6. Okay, don't just use the 3 that we use to calculate the height. You have to go use the entire base, which is 6. And the height is the square root of 187. Okay, so now it matters. Now you can put it in your calculator. 0.5 times 6 times 187 square rooted is 41.024. And we have square inches as your final answer. Okay, so this is good for all isosceles triangles. You're going to calculate the height most of the time by using the Pythagorean theorem. And then you're going to take that height in order to calculate the area. So hopefully you know that an equilateral triangle is also an isosceles. So when we draw the height here, and because it's equilateral, you can draw the height to any one of your sides. But just to stay consistent, let's draw it to the bottom, quote unquote bottom. We'll call this the base. Okay, so yes, it is still, the height forms two special right triangles. How do we know that these are special right triangles? That's the question. What are the angles of an equilateral triangle? 60 degrees and 60 degrees. And, well, what also happens is that the perpendicular bisector bisects that angle also, so this one has to be 30 and this part has to be 30. Okay, so in every one of these equilateral triangles, we have ourselves a special right triangle, a 30, 60, 90 special right triangle. Okay, so let's review real quick the information pertinent to our special right triangle. Okay, so if this is your hypotenuse, and it is, right, that's the hypotenuse of a right triangle, that means this side down here across from the 30-degree angle is your short side. Okay, that's the short side of your special right triangle. Do you remember how the short side relates to the hypotenuse? That's kind of what I thought. So I'll tell you, the short side is always half of your hypotenuse. Okay, the short side is always half. So let's explain that again. Right? If your height is the perpendicular bisector, then if this is your base, it got bisected. Right? So I can take this triangle, and what if I turn it this way? Right? Well, now that's the hypotenuse of a different height, and it got cut in half. So just remember that when you do your perpendicular bisector for an equilateral triangle, you are chopping right? This would be a potential hypotenuse somewhere. This gets cut in half. Okay, so that side is half of your hypotenuse, or half of the side length of your equilateral triangle. Because depending on where you draw your height, all of the sides could potentially be hypotenuses. So then the height, right? This is the height of your triangle in our case. This is the height. How much larger is the height than the short side, right? So there's, what am I trying to say here? This is the long leg of your 30, 60, 90 triangle, right? The height of your triangle is the long leg of your 30, 60, 90. So how much bigger is the long leg than the short leg? Which one of those funky roots was it? It was root 3 bigger. Root 3 bigger. So the height is always half of the hypotenuse times the square root of 3. Okay, so your short side is half of the hypotenuse, and your height is the short leg times the square root of 3. Okay, always. So let's put that into practice for a second here so we can see it working out. The height is always the long leg of a 30, 60, 90 triangle. The height is always the long leg of a 30, 60, 90 triangle. And as such, the height is the hypotenuse times the square root of 3 divided by 2. Okay, so that's the shorthand. You might want to memorize that and write it down 35 or 40 times if that's the way you memorize stuff. Right? Repetition, repetition, repetition is good for memorization. The height only for a 30, 60, 90, right? This is not good for any other triangle, but for a 30, 60, 90, the height is the hypotenuse divided by 2 times the square root of 3. So let's see if we can apply that to our next one here. Okay. Find the area of an equilateral triangle with a side length of 20. So let's see how good I can draw an equilateral triangle. Not very good. So 20 and 20 and 20, right? All sides are 20 with a 60-degree angle and every, so it's not necessary to draw your 60s, but just for fun. There we go. Okay, so we're going to call the bottom side your base. So this is your base. 1/2 of base, so 1/2 of 20. And now we're going to calculate the height. Okay, so let's do that using our special right triangles from before, our 30, 60, 90. So if we have a hypotenuse of 20, what is my short leg of my right triangle? That's going to be 10. Right, this much is 10, of course, because the height is a perpendicular bisector. So your base of 20 got bisected. So we have 10 on the right and 10 on the left. And then the height is the long leg. And the long leg is the short leg, which is, in this case, 10 times the square root of 3. Okay, so if you forget that, right, if you don't remember what that root 3 relationship is, you can still use the Pythagorean theorem. 10 squared plus h squared equals 20 squared, just like we did up above with all the other isosceles right triangles, or the isosceles triangles when we're finding the height of that one. Okay, so if you don't remember the root 3 relationship, you can still use the Pythagorean theorem in order to calculate that height. Okay, the only reason we would do that is potentially it could save you time, right? That's the only thing. If you remember the ratio, you save time calculating so that you don't have to go back and use Pythagorean theorem all of the time. Okay, so area is 1/2 of the base. The base is 20, and the height is 10 times the square root of 3. Now let's talk about two different types of answers. So let's do this one step at a time. What is 1/2 of 20? That's 10. So then what is 10 times 10? 100. So the exact answer was 100 times the square root of 3, which you might see on a standardized test like the ACT or the SAT or the PSAT, right? Something written strangely like that. Okay, which is probably not what you see if you use a calculator, but that's the exact answer. Because once you put root 3 in your calculator, now we have done an approximation. So let's see what your calculator says about 100 times the square root of 3. 173.205. Okay, 173.205 square millimeters. Okay, that's the answer that I'm looking for on these worksheets and assignments and Schoology things on your test. That is perfectly awesome to round that to 3 decimal places. You do not have to leave that with a radical. Okay, unless the problem says leave it as a radical, and then 100 root 3 is the correct answer. So read your directions in order to figure it out. Alrighty. An equilateral triangle has an area of 15.58846. What is the side length? All right, let's figure this out. Okay, this is also on your, will help you on your Schoology assignment tonight if you know how to do this. So do we know any lengths of our equilateral triangle? No, right? That's what we're trying to find. What is the side length? So all of these are x, right? We're trying to calculate the length of the side. And I would use s, but unfortunately my s's and my 5's look a lot alike, and it gets confusing. So I'm going to use x to represent the side length of my equilateral triangle. Okay, so let's derive the formula for any equilateral triangle if you know the side length. Okay? So area equals 1/2 of the base. What is my base variable? X, right? This is my base here. So 1/2 of x, right? That's my base. Now I have to figure out what my height is. Remember, this is my height. The height is the long leg of a 30, 60, 90 triangle. The long leg of a 30, 60, 90. Okay, so then if that happens to be 60, then what is the short leg of my 30, 60, 90 triangle if my hypotenuse is x? Right, half of x, or x divided by 2. Half of x, or x divided by 2. And I'm using x divided by 2 so that I can have one simple fraction when I'm done. Okay, so if that's my short leg, then the long leg is x divided by 2 times the square root of 3. So x divided by 2 times the square root of 3. So that's the height. That's the height. The half of the side length times the square root of 3. So that's x times the square root of 3 divided by 2. Right? Because over here I'm multiplying. I'm multiplying half of x times root 3 over 1. So it's numerator times numerator, denominator times denominator, which is why the root 3 is on top and not on the bottom. So let's see if we can simplify this. So we have one equation that you need to memorize by writing over and over and over again. Okay, so when we have a fraction times a fraction, you multiply all of your numerators together. So what is 1 times x times root 3? 1 times x times x. So what's x times x? X squared. And then I have times root 3. So there's no plus, there's no minus, there's no divide symbol. There's just root 3. X squared root 3. And on the bottom, I have two denominators. I have 2 times 2. So what is 2 times 2? 4. Okay? Commit this to memory. This will happen again and again in this class for the next week and a half, and even beyond. Okay? This is the area formula for an equilateral triangle if you know this side length. And only good for equilateral triangles. Don't use this for any other type of triangle in the universe, but use it for every single equilateral triangle. Okay, so now we're going to apply this equation or this formula to our problem. We know the area is 15.588 something, 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 something. So 15.58846. Right. Do all the decimals. Don't forget any decimals. Wow. Equals this formula. X squared times the square root of 3 divided by 4. You set the area equal to the formula, specific for an equilateral triangle. Okay, now this becomes an algebra problem. What is our first step in solving this algebra problem? Multiply by 4 the denominator, so let's times it by 4. Okay, so I hope you have a calculator handy to do this. Do not scrimp on the decimals. 58846 times 4 is 63.3538. Okay, once again, don't scrimp on the decimals as you go throughout this calculation. Okay, by the way, this right here, these 5, that is an approximation, so your answer is not going to come out within a perfect number, I don't think. But it's going to be close enough where you can round to the perfect number. Okay, what's our next step here? X squared times the square root of 3. What's our next step algebraically? Well, I guess I'll just tell you. Divide, right? This is a division problem because we have x squared times root 3. We're going to divide both sides by root 3. Right? Root 3 is a number. It's not a number we encounter very often, but it is in fact a number. So when I do 62, wait, that was 62, so sorry, 62.3538, 62.3538. When I divide that by the square root of 3, I get exactly 36. Exactly 36. So now my final step is to take the square root of both sides, because you don't ever want to square root something other than just x. And I have a side length of 6 inches. Okay, 6 inches is my side length. So this purple equation here is very important. Make sure you have that written down somewhere. I'm going to have it in a poster in my room, of course, because that's what I do, because I can't remember things very good. So if I see it on a poster, then I am more able to memorize it. Okay? You are more than welcome to make your own poster and put it in your own room and be really dorky about it. Okay? So when we have an isosceles or an equilateral triangle, the height is the perpendicular bisector. Okay, so your base gets cut in half, and you can use the Pythagorean theorem in order to calculate the height. Okay? So hopefully that helps you do these problems for today.